In this video, we will cover an implementation of Pyspark Estimators. Estimators are a Pyspark class that takes as input a data frame and returns a transformer. Both estimators and transformers form the two key building blocks of Pyspark pipelines, which are a highly scalable and modular way to organize a project's codebase. Pyspark comes with a suite of native estimators that you can choose from. However, in this video, we will work through building our own estimator from scratch. All coding shown in this video is done in a Jupyter notebook available on my GitHub. You can find a link to this notebook in the description below. Okay, so now we're in a Jupyter notebook where we'll work through our implementation and example for the estimator. Just note that I have corresponding notebooks for both working through Pyspark Pipelines and Pyspark Transformers. And I also have accompanying videos for those two topics as well. I have links to all of those in the description below in case you haven't seen those videos yet already. Okay, so we'll begin now by running these first two cells that will load in all the modules that we will use, as well as create our Pyspark session. Okay, and now what we can do is load in our data. So like the previous video on transformers, here we'll use the California housing prices data set. This is available from scikit-learn, and we can get these data by just calling this function. And we also split it up based on input predictor features and the target label as well. So we can take a quick look at the predictor features, and here we can see that there are a total of 8 features that we will have to work with. So now let's get a sense for how these features are distributed. So we can produce this box plot, and right off the bat we can see that these features are not on the same scale. In particular, we notice that the population has a much larger scale than the other features. Now, for the purpose of this example, we are going to use a linear regression to try and predict the median house price. And because we're using a linear regression, we're going to need to have all these features on roughly the same scale. Now, for doing this, we're going to need a model to do the standard scaling. And in fact, that's what we're going to build an estimator to do, is to simply scale these features all to the same level. So before we proceed on to that, the last step we're going to need to do is run this cell, which will attach the label back with the predictor features, and then we're going to create a Pyspark data frame off of the pandas data frame. And here we see the output, so everything is in Spark now. Okay, so now we can proceed with our implementation. So as mentioned at the beginning of the video, an estimator takes in a data frame and returns a transformer. So the first thing that we need to do is to define our output. We're going to implement the transformer first. Then once we have the transformer, then we can go back and actually build the estimator. So in this case, the estimator is going to be called Custom Standard Scaler. That's what I've decided to name it. And the transformer that it outputs will be called Custom Standard Scaler Model. Okay, so now let's begin by defining the transformer. So here is Custom Standard Scaler Model, and we can see it's a transformer because it inherits this base transformer class from Pyspark. So we inherit from this. We also have two mixins that define the two of the input parameters we're going to use for this transformer. So a set of input columns and a set of output columns. And as well, we also have these classes, the default params readable and default params writable. And these are necessary just to enable us to be able to write this transformer to disk. So the first thing we do right off the bat is define our custom input parameters. And in this case, it's going to be a list of means and a list of standard deviations for all the different features that are in our data. So these are custom definitions. And then in our initializer, here we see all the input arguments to the transformer. So we've got a list of input columns. That's the list of raw features coming in. The output columns, which is the list of now scaled features going out. And then we have a list of means and a list of standard deviations to do the scaling. Since what we want to do for all of the features is to scale it such that we can possibly have a mean of 0 and a standard deviation of 1. That's why we need to have these means and standard deviations to do the necessary computations. So the rest of the init is just setting the default values for these parameters. And the only thing that we really need to implement here is the set params function here below. So in set params is defined here. Now following along with how a transformer is typically built, we also have to implement the set and get methods for each custom parameter. So in our case, there's going to be a total of 4 of these. And this is simply boilerplate code that is fairly standard for or when building a Pyspark transformer. So we need to have these methods in place. And we use the get methods actually within the transform method. The transform, or the underscore transform method, is where our actual logic takes place. And you'll notice here that we take in a data frame and we're going to return a data frame as well. The arguments or the input parameters for the transformer are read in here through the get methods. You may wonder why we have to read in the input parameters by using the get methods as such, but this is necessary with Pyspark in order to be able to write the transformer to disk and then load it back up again. So this is simply just how Pyspark works. So once we've read in our parameters, we can loop over all the different combinations. And then for each feature, we simply subtract out the mean and divide by the standard deviation. You can see that right here. And that will perform our scaling. So this is all the logic we need for the transformer. So now we'll proceed on to define our estimator. That is custom standard scaler. It inherits from the Pyspark base class Estmator. And we also take in the same other classes as previously with the transformer. So that is the input calls, output calls, default param readable, default param writable. Now the job of the estimator is to learn what the means and the standard deviations should be. So if you remember from in the transformer, we use these lists of means and standard deviations in order to compute the scaled features. So that's what's happening right over here. But you might ask yourself, well, how do we get these means and standard deviations? Well, that's the job of the estimator. Now in this case, what we're going to do is we're going to include 2 custom parameters, and these are going to be Boolean parameters that will allow the user to choose whether we want to scale with the mean and with the standard deviation. So if you want to scale to both a mean of 0 and a standard deviation of 1, you would set both with mean and with STD as being equal to true. Otherwise, if you want to have any other combination, you can set the respective parameter to false. So that's what these parameters will do. And now we can define the initializer for this class. So like before, this is pretty similar, except that now we have these two Boolean arguments instead of the lists for the means and standard deviations. But all of this is fairly similar. We're just setting the default values. And like before, we set we have the set params function to set the default values itself, and that's called within the initializer. And again, like before, for each of our custom parameters, we have to build a set and a get method. So because we have two custom parameters, we're going to have a total of 4 of these methods. And that's what's implemented right here. And now finally, so with an estimator, we have a fit method instead of a transform method. And fit is just going to try and learn the parameters that we need to learn in order to build our transformer properly. So the way that we build our fit method is just by having this function underscore fit, and that is going to take in a data frame here, df, and return the transformer custom standard scalar model. So that's simply how that's built. Like before, we read in our parameters using the respective get methods. And then now we can perform our logic. So the first block of code here checks our input Boolean. So if with mean is equal to true, then we're going to compute the mean for each of the input columns. And that's what's performed here. Otherwise, we set the mean to 0. And so that just basically cancels out any of the effects of the scaling logic. Likewise, for the standard deviation, we're going to do the exact same thing. If the parameter with std is equal to true, then we're going to compute the standard deviation for each one of the input columns. And that's what's performed right here. Otherwise, we set the standard deviation to 1, which cancels out the effects of the standard deviation within the scaling. So once we have all of this in place, we can then return our transformer. So we return the custom standard scalar model with the list of input columns as received, the list of output columns also as received previously, and now our lists of computed means and standard deviations. So we can run this cell. Oops. I didn't run the transformer yet, so let's run this. And now we can run the estimator, and that fixed it. Okay. And so now let's just work through a quick and simple example to ensure that everything is working. So the first thing that we can do is get a list of input columns that we want to have scaled. And I'm also going to prepare a set of output columns that should be the output from our scaling operation. And now I'm going to declare an instance of our scalar. So that's going to be right here. And I'm going to scale with both the mean and the standard deviation. Okay, so now we've got an instance of our estimator, and I will use the fit method to train the scalar on our data. Okay, and now scalar model is a transformer that will be able to perform the scaling operation that we want. So this fit method has just learned the means and standard deviation parameters that we need, and now we can actually perform the scaling that we want. Now, if we want to check what the learned parameters actually are, we can use those get methods to view them here. And we can take a peek at those, and these values look pretty reasonable, look like what we would expect. So it indicates that our estimator is working. And now we can perform the transform method on the output scalar model to actually scale the features. And now, just to verify, we can produce a box plot to see if the features are scaled. And we can see that, yeah, they look pretty scaled. It looks much better than before. So that's great. It shows how we can build a custom estimator. Now, the next part of this video, I would like to show you how we can integrate this estimator into a Pyspark pipeline. So let's proceed on to that. So for this part of the notebook, what I want to do is split up the data into a train and test set, with 80% of the data going for training and then the remainder for test. So let's do that right now. Okay. And now I'm going to construct a very simple pipeline that will attempt to model how we can predict the median house price based on the set of input predictor features. So like I mentioned earlier before, we're going to use a linear regression model here. So we've got this pipeline with 3 different stages. The first stage is our scaler. The next stage is a vector assembler, and this is a Pyspark transformer that comes natively with Pyspark, and that's just going to collect up all the input features and place it in a single column called features in this case. And the final stage in the pipeline is the linear regression. This is also an estimator, and it is going to take the features column and attempt to learn the parameters for predicting the label column, which is the median house value. So we've got a pipeline here of 2 estimators and 1 transformer. So we can run this to define the pipeline instance. And now we are going to call this fit method on the pipeline. So what this is going to do is it's going to execute through each one of the stages of this pipeline, and wherever there's an estimator, it is going to execute the fit method and then yield the output transformer. So model here is going to be essentially another pipeline, but now with just 3 transformers. So we can run this. Okay, and now with model, we can run the transform method to pass through each one of the stages and get predictions on our test set. Okay, so now we can compare how our predictions are compared to the true values for the house prices. Okay, and it's not the best model, but these values are not unreasonable at all. And we can see here that the mean squared error is 0.5, which is not so bad. That's reasonable. So that demonstrates how we can use the estimator in a pipeline. The last thing I want to show you, I want to at least demonstrate and prove to you, is that we can take this pipeline and write it to disk and then load it back up again. Now, you might ask, why are we interested in this at all? Well, it may be the case, for a more complicated model in a much larger project. Training can be very expensive in terms of time and also money as well. So we may not want to do that all the time. So if we have a training phase that takes, say, several hours and computes a lot of resources, we may just want to store that trained model for use later whenever we need to generate predictions. So that's the main use case for writing these pipelines out to disk. So that can be easily done. Here we've got our model again. This is the trained model. And we're just going to write it out to disk by calling this cell. So write, overwrite, save. And we're going to save it to this folder, trained pipeline. And now we can load it again by calling the load method on a pipeline model. We've loaded it back up. And now let's just use the loaded model to perform predictions, again, right off the bat, and then compare the results. Okay, and we can take a peek at these numbers. We can look back above. We can see that these are actually the same set of numbers. So this shows how we can save a trained pipeline to disk that includes our custom estimator and load it back up again for use at a later time. So that concludes this video. I hope you learned something and got some value from this demonstration. If you like this content, please like, share, and subscribe to the channel. It's always appreciated. Have a great day and see you in the next video.